Hi, welcome to next session of understanding elements of programming. Here we will first do the revision of what we covered in the chapter 2 and then we continue with our current session. So yesterday we covered the concept of transformation, where transformation is nothing but a mapping from type T to T, and it is a regular function as per our earlier commitment that in the entirety of the book we will only focus on the regular functions. And we saw the definition of predicate. Predicate is nothing but a regular function whose output type is either true or false. Then we covered partial and total functions, where total function are those where definition space is equal to domain, but in partial function it is not necessary that domain space equal to like definition space equal to domain. And you were encouraged to refer to the meaning of non-total functions as well. And next we covered a definition space predicate, where definition space predicate is defined on same set of values as the domain of function, but the definition space predicate is always defined. Like basically, if the our function is partial function or non-total function, then it is possible that for some elements in the domain, the function is not defined. But definition space predicate is defined for all such possible values in the domain, and it returns true if we can call function on the input values. Otherwise, we may or may not be able to call the function. It means function may give correct result, incorrect results. We don't know. We don't care. We only care about the definition space predicate. If like we only care about the function if definition space predicate gives true, because in that case we are guaranteed that function will give correct answer. And we covered one example of a plus b, like sum of two's complement 32-bit integers, and how to write their definition space predicate. Next, we covered transformations and their powers, and we established the correspondence between integers and powers. Basically, computing nth power is equivalent to going to nth integer from 0. So, effectively, in terms of complexity, like time complexity and computation complexity, computing nth power of computing application of function f nth time is same as order of n, because we need exactly n steps to reach the function. There is no scope of improvement here. If we know some other properties of function, maybe those can help, but uh, with the minimum baseline, this is the time or number of operations we have to do to compute the nth power of f. Then we consider the power algorithm and how it is defined on the generic inputs, and one of the parameter which was the starting element x. The type of parameter is dependent upon type of transformation and the integer type which we are using. Then we covered the concept of orbits, where we talked about reachability, like one element is reachable from other if after applying at least one or at least zero application of the function, we can reach the element. Then we covered the cyclic structure. We covered terminal element. Terminal element is that element which is the result of some transformation, but we can't apply further transformation to that element. Then we covered the concept of orbit. For a given starting element, the orbit is basically set of all the possible values which we can get. And distance, we saw that distance is a directed function. Basically, distance of x comma y may not be equal to distance of y comma x. And if our structure is not cyclic, only one of distance x comma y and distance y comma x is defined, assuming x is not equal to y. Like if x is equal to y, then distance is defined as 0. In that case, it is reflexive. Then we covered the distance algorithm, which was trivial, so we can skip this. So we had four types of orbit. One is infinite orbit, one was terminating orbit, one was circular orbit, and one is rho-shaped orbit or p-shaped orbit. This is the structure that we have to keep in mind from global perspective. Like if we have a transformation, the transformation with a given static element can produce any of these structure. It is not possible to generate any other type of structure because we have exhaustively covered every possible case. So we had the definition of finiteness, cycle, handle, connection point, and orbit, handle, cycle size. These things we covered. Now in this session, we will see how to compute the handle size, the size of cycle, how to compute the connection point or the value of connection point. And Yeah, so let's get started. So to determine the collision point, let's take a very general case of p-shaped handle or like p-shaped orbit. And also we are assuming that we are not handling this infinite case. Our algorithms will work on these three types of cases, and we are assuming that no infinite case can occur. Okay. So to compute the collision point, we will go with one algorithm, one particular idea of algorithm. It is not necessary that this algorithm is the correct one and no other solution exist. But as per the book, we will only discuss about one algorithm, and that algorithm is the algorithm of fast and slow pointers. If you go over Geeks for Geeks, you will see finding cycle in the linked list using this algorithm as well. So, what is the idea? The basic idea is that let's say this is a structure of our orbit, okay, and we have two cars starting from initial starting element. One is denoted as slow car, and one is fast car. And what is the property of slow and fast car? In one step, slow car moves forward one direction, and in one step, fast car moves forward two steps, not direction, two steps. Or basically, speed of fast car is twice the speed of slow car. And the general idea is that if we have this type of structure where either we are in p-shaped handle or we are in circular orbit, after finite number of steps, these two cars will meet inside the circle at some point. Let's say this is the point where they meet. Okay. So the point where these slow and fast car meet, that point is known as collision point. Okay. We have defined two types of points. One is the connection point, the point where handle and cycle meet. Hmm. And one is the collision point. Collision point is where this specific algorithm of fast and slow car, if we iterate over, if we apply this algorithm on the transformation, the point where they meet is known as collision point. And it is guaranteed via this algorithm that such collision point will exist. Like it is not possible that slow and fast car will never meet. That is not the case. Okay. So let's say in our entire discussion, we will denote by n number of steps taken by slow car to reach collision point. Okay. So now we have two choices for the fast car. If we assume, like by usual, we denote that 2n will be the number of steps taken by a fast car to reach the collision point, then we have to take care of the case where n is not equal to 0, right? Because for n equal to 0, both are at starting point. So one formulation will be like this. Second formulation, which is chosen by book, is that we start with one step on the racing line. So basically, let's say this was the starting point and these were the subsequent nodes. Slow car will start from the first point, while the fast car will start from one point ahead, such that whenever they will meet with n greater than equal to 0. Like in our conditions, we can simply put n greater than equal to 0. We don't have to take care of special case for n equal to 0 in our analysis. But both approaches are correct. In one first approach, both cars start at same starting point. But in second approach, fast car had a jump start, like it started with one element after the starting element, and then the algorithm starts. Okay. So as per the book, we will go with the second approach where fast car had a head start of one element or one node. So if we have such a condition, then we know that collision point is nothing but basically nth application on the x, which is same as 2n plus 1th application on the x, where n is greater than equal to 0. This is our definition for collision point. And n is the minimum such integer or natural number where this happens. Okay, this is our definition of what is a collision point. So, how to compute the collision point? The algorithm is very trivial and is as specified. So, let's say we have a starting element and we are open to various cases. Ignoring the infinite case, which we are not covering, we either have a terminating case where, let's say, transformation or orbit only have three elements with no cycle, or we have a cyclic structure, or we have a handle with cycle. So, this collision point algorithm, as per the book, will return these things. So, if it is a terminating case, it will return the final element. If cyclic structure is present, any node will be returned in that case. Why? Because it is not necessary that the fast and slow car will always collide at the starting point in the total cyclic case, and it is not necessary that fast and slow point collide on the connection point on the handle case. So basically, collision point algorithm only have two guarantees: either we reach the end point or we are inside the cycle. Which node, we are not sure. We will do analysis later, which is the node, but that is the guarantee from the collision point algorithm, and we have to further distinguish between the cases based upon the result. So let's say one case is very basic case that we have a starting element, but we can't even apply the function f on it. So this comes under the terminating case, and we will simply return x. Here we can see we are checking whether we can apply a function or x or not. So first we check that okay, we can't even apply the function on x, we simply return x. Next, so now we know that we have at least one element. Either it is cyclic or we can move forward. So let's say our slow car starts at first point, and as per our earlier assumption that fast car will start 1 point ahead from the slow point. So this is the assumption. Like slow point is f0 of x, which is x, and first point will be at f1 of x. And we know that f1 of x exists because we came here only after checking that we can apply function on x. So we move until first is not equal to slow. So this is the loop invariant that we maintain throughout the loop. That if after n steps my slow pointer is at f of n x, then our first pointer will always be at f of 2n plus 1x. It is very simple. We first move slow one step, and we have to move first two steps. So we first check if we can move first, we apply first. Then we check again if we can apply first, we apply first. Otherwise, if we have reached the endpoint, we simply return the first, denoting that we are in the terminating case. We don't have any cycle, so we can simply return here. Okay, and it a very trivial question and easy question arises: why we don't have to check for any p condition or predicate condition while moving the slow pointer? This is very trivial. I am not going to cover it. Okay, so when this loop breaks, we know that we are at a collision point. We are inside a circle. How? Because if we were in a ending point, or like we reached the terminal point, we would have returned with these return statements. So we are here. It means we are inside the circle and we are simply returning it. And post condition is that the return value is either the terminal point or we are in the collision point. Where collision point is this is returned by this first return, last return statement. Okay. So now coming to the mathematics of collision point. So I am not going to cover the exact details of how these results are derived. You have to refer to the book. I will simply going to cover the main results of what is being said or what is being derived. So we have derived the collision point. So let's say in general case we have this handle and we are here. As per the book's notation, this is the handle size h. The number of elements is c such that O plus h equal to c. So let's say this is our, to make it discrete, let's say this is our structure. For this case, handle size equal to 2 and number of elements in the cycle equal to 2 and total number of orbit size, like orbit size equal to number of elements, which is equal to handle size plus c. Okay. So as per the book definition, this is the d. Like if we have are at connection point, then the distance between connection point and collision point is denoted by d, and distance between collision point and coming back to the first connection point is denoted by e. This is the notation used in the book. And as earlier stated, I am not going to derive these the results. I will simply state them here. Okay. So first we okay, so we have to determine three things: cycle size, handle size, and connection point. So how do we determine? First, uh, I will determine the cycle size, which is very easy. So how to determine the cycle size? Let's say we are at this position, both first and slow pointer at this position. To determine the cycle size, we simply have to move slow pointer and n number of times, where n will give the cycle size, right? So we will put first pointer here, and we will move slow pointer uh, one step at a time, and we count how many steps it took to reach the first point again, and the number of steps will be equal to cycle size. Very simple, nothing to do here. Now coming to handle size and connection point. So a result is derived in the book which says, and you have to understand this very carefully. So let's say x was the starting element and y is the collision point. What is the collision point? Like, where is it? It is inside the circle. So result is that if I apply function f h number of times to the initial starting element. So let's look at the example here again. Let's say we have three elements in the handle and two elements in the cycle. So this is the structure. This is x. Handle size is 3. So after applying the function three times on the x, we will reach the connection point. Okay. And the result says that it is equal to applying, like moving h plus 1 times from the collision point. Basically, if x and y are our starting point, what we can do, we can apply f on y once, and then we iterate in a loop till they meet, and the point where they meet is the connection point. This is the algorithm, like this is the result from mathematics. Okay, so you are encouraged to look into the proof, and here I will simply state the results. So we have only three things: cycle size, very easy to determine. From collision point, we simply go again and we count how many steps we took to come back to the starting point in the collision point, like in the cycle, or to the first pointer. Very simple. And using one result, we were able to compute the handle size and compute connection point. Basically, go to the starting point and go to the collision point. Move one step from the collision point, and then move both points one by one. So basically, apply function on x and y simultaneously, and count how many steps we took till they meet. So they will meet at a common connection point, and the number of steps we took on x on the starting element will be handle size. Okay, so we have determined the structure. Now in section 2.4 of the book, above results is implemented, but they are making some point. The author is making some point regarding how many, like we can't simply return h for the handle size, we have to return h minus 1. What is the reasoning behind it? So let's say we have our type t, like function is applicable from type t to t. Okay, and total number of possible values type t can take is, let's say, k bits, is representable in k bits. Or without going into bits, let me keep it more general or more clear. Number of possible values type t can take is, let's say, n. Okay, so let's have a very simple example of terminating cycle case, like terminating orbit, where let's say n equals 5. So what are the possible values of handle that we can have? We can either have handle size of 1, or handle size of 2, or handle size of 5. In this case, going to one extreme, let's say we have 5 elements in a cycle. This. So how many distinct values the cycle can take here? Also here, handle can take these many values, and cycle size has to be 0. In second case, handle size is 0, but cycle size can either be equal to 1, cycle size can be equal to 2, 3, 4, 5. Again, let me be more clear. It is the number of possible values type T can take. It is not necessarily equal to, like, it does not necessarily mean that from starting point we can cover all these nodes in the type T. Okay, you are aware of any such example. So let's say we are taking transformation f of x equal to 2x, and we are, like, our starting point is, let's say, x equal to 1, and we are in 32-bit unsigned integers. So with this, so how many elements we have? Our n equal to 2 raised to power 32. But we are not able to iterate over all the elements with this given starting element and with the given transformation. So that's why I have written these possibilities, that cycle size can be 1, 2, 3, 4, or 5 if we had 5 elements, and this is the maximum possible case. We could have this case, we could also have this case, and we could also have this case. Okay, and again, fourth case, it is also possible with 5 elements. So what we can see, that with 5 elements, h can take 0 value, h can take 1 value, 2 value, 3 value, 4 value, and 5 value. So number of possible values h is how many? N plus 1. Similarly, number of possible values for c is n plus 1. Here we can see c can either be 0, 1, 2, 3, 4, 5. While our n was 5, c can take all the possible values from 0 to 5. So number of possible values for c is n plus 1. And for the handle case, where let's say h is greater than equal to 1, we know that number of possible values for handle is less than equal to n, because we have at least one element in the cycle, and number of possible values of c is less than equal to n, because we have at least one handle element, or strictly less than n. And for h, it has to be strictly less than n, because one element is part of cycle. So this is the discussion in the book, where let's say 2 raised to power k plus, like, if n is a perfect power of 2, then instead of returning all the possible values of h, let's say from 0 to 2 raised to power k, we return all the possible values from 0 to 2 raised to power k minus 1, or basically 0 to n minus 1. We never return the value n for h, because we can't represent it in the same number of bytes. We have to expand our byte storage, or basically number of bits we have to represent the value h is greater than number of bits required to represent all the possible values n can take. So to save the space, the author has decided to go with the implementation where we only take as many bits required, as many bits to represent all the possible values that I can take. And you can go over exact implementation details and main argument, how it is defined. Okay, so coming to actions. So what are transformations? Transformations is simply a function that for a given input type returns type T. What are actions? Actions are nothing but simply void function. Like, they are of this format, where we start from, they take one argument, basically let's say T value, and let me open the book for you to show you how they are defined. And we opened elements of programming here. So we covered measuring orbit size and all the possible cases, and these are actions. So if algorithm use transformation in a statement like this, now here f is a function which takes a element x of type t and returns type t. Instead, we can have an action where we take type, like, t value as a reference, and we internally state it, like set its value with the application of function. Like, instead of returning, we have modified the value in place inside the function itself. So these two implementations are equivalent, and there is nothing new here, like nothing new to see, only that the implementation is somewhat different, but net result in both the cases is same. Okay. And there is a very good algorithm, like very good exercise in this chapter that you are encouraged to refer to. The question is, design an algorithm that determines, given a transformation and its definition space predicate, whether the orbits of two elements intersect. Basically, we have a function like transformation f, its definition space predicate p, and two values x and y in the domain of f. And we have to return true or false if their orbit have some common element. Okay. And there is a lemma before this relating to this, like if the orbits of two elements intersect, then they have the same cyclic elements. Very easy to prove. So you are encouraged to go over this exercise and obviously through all the exercises as well. So we have covered actions, transformations. So yeah, we have completed this chapter. In the next session, we will cover associative operations, where by associativity we mean that if star is an operation between two elements A and B, then this thing equal to this thing. Or it means we don't care how in what order we apply the operation, we will get same result. One counter example to this is vectors dot product in vectors, or let's say minus in integers. Very simple example. So let's say our operation is minus, and these two things are different, as we know, right? Because left hand side is same as -1 -4, and it will be equal to 1 minus of -2, and which will be equal to -5 equal to 3, which are not the same. So we say minus is not associative. It matters in which order we apply the operation of minus if we have two consecutive minus operations. But in case of, let's say, plus or multiplication, it does not matter. So if we are in the domain of associative operations, we will see at an algorithm to compute, let's say, a star a, which is given n times in log n time, assuming that a star a can be computed in O1 time. Under this assumption, we will see how to compute n such multiplications of element a with itself in log n time. Okay. See you in the next session.